Hi everyone, my name is Zhentang Zhuang from Yale University. It's a great pleasure to share our work, AdaBelief Optimizer, adapting step sizes by the belief in observed gradients. First-order gradient optimizers for deep learning can be categorized into two types: the accelerated gradient methods and the adaptive gradient methods. The SGD family typically has a good generalization, but suffers from slow convergence and instability in complex settings. The adaptive family typically has a fast convergence and stability for complex settings, but typically suffers from a poor generalization. So in this work, we propose an optimizer that achieves fast convergence, good generalization, and training stability. Our method is called AdaBelief. Compared with Adam, it basically uses a centered second momentum for update. We use GT to denote the gradient at step t, and use MT to denote the exponential moving average of GT. In Adam, the update is divided by square root of Vt, where Vt is the EMA of GT squared, while in AdaBelief, we basically replace Vt by St, where St is the EMA of GT minus MT squared. So why do we call it AdaBelief? Basically, we can view MT as an approximation to the predicted gradient. If the observed gradient GT deviates much from the prediction, then we have a weak belief in observation and take a small step. If the observation GT is close to the prediction, then we have a strong belief and take a large step. Let's look at an intuitive explanation for the advantages of AdaBelief. On the left is the loss function f with respect to parameter theta. Suppose we start from theta 1 and reaches theta 2 and theta 3 in the next two steps. In this region, the amplitude of the gradient is small, and the amplitude of the difference in gradient is small, and current step size is small. An ideal optimizer in this case should take a larger step size. Now let's take a look at three different optimizers. For SGD, its update is proportional to the exponential moving average of the gradient. Because the amplitude of the gradient is small, hence SGD takes a small step. For Adam, it is divided by the square root of the EMA of GT squared. In this case, since the amplitude of gradient is small, then the denominator is small, hence Adam takes a large step size compared to SGD. Similarly, for AdaBelief, the denominator is small, it takes a large step size. Let's take a look at the region 2. Suppose we start from theta 7 and reaches theta 8 and theta 9 in the next two steps. In this case, the amplitude of the gradient is large, and the amplitude of difference in gradient is large. In fact, the gradient changes its sign, and the current step size is large, hence we observe an oscillation phenomenon. In this case, an ideal optimizer should decrease its step size. Now let's take a look at the different optimizers. For SGD, the update is proportional to the amplitude of the smoothed gradient, hence the step size is large. For Adam, it is divided by the square root of the EMA of GT squared, hence the denominator is a large number, and the next step size is small. Similarly, for AdaBelief, the denominator is large, hence the step size is small. In region 3, suppose we start from point theta 4 and reaches point theta 5 and theta 6 in the next two steps. In this case, the amplitude of gradient is large, but the amplitude of the difference in gradient is small, and current step size is small. An ideal optimizer should increase its step size in this case. Now let's take a look at three different optimizers. For SGD, its update step size is proportional to the EMA of GT. Because GT has a large amplitude, hence the step size of SGD is large. For Adam, it is divided by the square root of GT squared. Because the amplitude of G is large, hence the denominator is large, and the step size for Adam is small. For AdaBelief, because the difference in gradient is small, hence the denominator is small and the step size is large. So for all these three cases, AdaBelief is the only optimizer that matches the behavior of an ideal optimizer. Now let's look at another example. In case 1, the linearity is small, and the gradient in theta 1 is close to the gradient in theta 0, while in case 2, the linearity is large, and the gradient in theta 1 has different sign from the gradient in theta 0. Now let's take a look at Adam. Because the denominator in Adam is the smooth version of gt squared, hence it is insensitive to the sign change of the gradient. It is only sensitive to the amplitude of the gradient. Hence, it cannot differentiate between case 1 and case 2 in the denominator. While in AdaBelief, the denominator is the difference between gt and mt in the squared. Hence, the denominator in case 1 is smaller than the denominator in case 2, and the step size in case 1 is larger than the step size in case 2. Now let's take a look at an example. In this case, the gradient in x direction does not change its sign, while the gradient in the y direction keeps changing sign. Hence, we observe an oscillation in the y direction. In this case, AdaBelief takes a larger step size in x direction and a small step size in y direction, hence reaches the optimal very fast, while Adam and SGD takes similar step size in x and y direction, hence they are slow. Next, we show that update direction in Adam is close to sign descent for low variance case. Under the following assumptions that GT is drawn from a stationary distribution, and we assume the variance in GT is low compared to the amplitude of the expectation of GT. Also, we assume beta 1 to the power of t is small, hence MT as an estimator of the expectation of GT has a small bias. In this case, the atom behaves like a sign descent. In 2D cases, which is the 45 degrees to the axis and deviates from the true gradient direction, while in AdaBelief, it takes a small step if the variance is large, and it takes a large step if the variance is small. Next, we take a look at a toy example. We set beta 1 to the power of t at a small number, so that mt as the estimate of the expected gradient has a small bias. In this case, Adam behaves like a sign descent in the early phases, while SGD and AdaBelief updates in the direction of the gradient. Here are two examples where AdaBelief outperforms Adam and SGD optimizers and reaches the optimal point at the fastest speed. Here are another two toy examples where different coordinates are highly correlated and ill-conditioned, which is often the case in deep learning, and the local behavior of AdaBelief in these examples give hints to its behavior in high-dimensional cases. We validate AdaBelief on image classification tasks. On CVI-10 dataset with different models, AdaBelief achieve the highest accuracy at a high speed, and on ImageNet dataset with the ResNet 18 model, AdaBelief achieves a comparable accuracy to SGD and significantly outperforms competing adaptive methods. We then performed experimentation on LSTM models. For different layers of LSTM models, AdaBelief consistently achieves the lowest perplexity. We then validate AdaBelief in the training of GAN, where optimizers such as SGD often fail. We experiment with the WGAN on CVI-10 dataset. The GAN model is small with a vanilla CN generator, and compared to other optimizers, AdaBelief consistently generates the lowest FID score. We then experiment with a larger spectral normalization GAN with a ResNet generator. Because the model is larger, so the result is better, and the overall FID compared to the smaller GAN is lower. In this case, comparing with different optimizers, AdaBelief still generates the lowest FID score. We then performed extra experiments with neural machine translation using a transformer, and AdaBelief achieves the highest blue score. In summary, we propose AdaBelief, which adapts the step size according to the change in gradient. We validate AdaBelief with extensive experiments, and AdaBelief achieves fast convergence, good generalization, and training stability in complex settings such as GANs. We provide a Python package for AdaBelief optimizer. Next, let's take a look at the package implementations and extra experiments. First, let me thank all the contributors and also the inspiring discussions on GitHub, Reddit, Twitter, Zhihu, and WeChat. Here are general principles to use AdaBelief in your experiments. The first principle is to check if their code is from the latest official implementations. The default hyperparameters in the latest implementation, which is version higher than 0.1.0, it uses different default hyperparameters from the old version, so it's really important to check which version are you using. The second principle is to check all the hyperparameters. Do not simply use the default. Keep in mind that epsilon in Adam is different from the epsilon in AdaBelief. Typically, if you want AdaBelief to behave similarly to Adam, then the epsilon in AdaBelief should be roughly the square of the epsilon in Adam. This is because epsilon is used within the square root in AdaBelief and is used outside the square root for Adam. The general principle is if SGD performs better than Adam, then you use a large epsilon. If SGD performs worse than Adam, then you use a small epsilon. And in this case, often the rectification helps. We recommend two values to try for epsilon. If SGD is better than Adam, then we recommend to try 10 to the negative 8 for epsilon. Otherwise, we recommend 10 to the negative 16 if Adam performs better. And the third point is to check all the hyperparameters. And please refer to our GitHub page for a full list of recommended hyperparameters. So here is a table of hyperparameters to reproduce the results in the paper. There are two hyperparameters, which is the last two columns, is called fixed decay and AM squared. They are always set as false, so we don't need to care about them. We really need to care about the parameters is epsilon and the weight decouple. Remember that if SGD performs better than Adam, then try a large epsilon, let's say 10 to the negative 8. If Adam outperforms SGD, then we recommend to try a small epsilon, such as 10 to the negative 16. In practice, you can just try these two numbers, 10 to the negative 8, 10 to the negative 16. If you want to fine-tune, you can try some numbers such as 10 to the negative 12. The learning rate beta 1 and beta 2 are just set as similar to Adam. The weight decay value really varies from experiment to experiment and also varies with structure, so there's no general point for that. But for all our experiments, the weight decay is set at the same for Adam. Now let's take a look at extra experiments. So first, on WeChat, some users said FID score is too high compared with SOTA for our GAN experiments. Our response is this is because the original GAN model is too small in our experiments. The high FID is due to the model rather than the optimizer. So we actually trained with a larger spectral normalization GAN, and the results are shown below, where AdaBelief achieved significantly lower FID score. And this is roughly the state of the art, which is under 20. Compared with our original version of GAN, which achieves FID of, let's say, above 30 or 40, this is because the model is really different. The table shown here uses a model that takes roughly 15 hours to train 100 airbags, while the original version takes only half an hour to train for 100 airbags. So the real difference in FID is caused by the model structure instead of the optimizer. And when it's trained on the same model, our optimizer outperforms other optimizers for both large model and smaller models. And the hyperparameters is shown in the table below. All the parameters are just taken from the hyperparameters for Adam. Next, we performed extra experiments on transformer. We actually tried two different implementations and with links and results shown here. So for both cases, AdaBelief achieves higher blue score than Adam, and perhaps Adam. For the first implementation, it's achieved slightly lower blue score compared to AdaHashing. This might be because that AdaHashing used some tricks such as block-wise averaging during update. This trick perhaps can be applied to AdaBelief, but it takes quite some effort in coding. And we also list the NeurIPS and other hyperparameters here. Next, we thank Yuanwei 2019 for conducting experiments with object detection using faster SAN FEN on Pascal dataset. The MAP is shown in the table here, where AdaBelief achieved the highest MAP of around 81.02. The model structure is taken from the official implementation of MM detection repository. The default is trained with SGD, and the result is around 79.5 for the MAP. And AdaBelief achieves slightly better results than this one. eAdam is an optimizer proposed by Yuanwei, which is just a modification of AdaBelief, where the gradient difference is replaced with a gradient square, and the epsilon change between AdaBelief and Adam is just kept in eAdam. So this experiment shows that epsilon is quite important for this particular task on Pascal object detection and perhaps with image detection. But this eAdam optimizer is not extensively validated on other experiments such as GAN training and transformer. We also conducted extra experiments with reinforcement learning using the soft actor critic model. This experiment is performed by Moonpen, a user on Twitter. Note that the orange curve is not the official implementation of AdaBelief, and the non-official version uses EPS like 10 to negative 3, which is quite large because the official uses like EPS 10 to negative 16. The green curve is the result for the official implementation of AdaBelief, and it can be shown that in this case, the Adam and AdaBelief have quite similar performances. Also, based on the same model, we conducted slightly extra experiments by tuning the EPS. So the default EPS is 10 to negative 16. When we set it as 10 to negative 12, we only plot the results between Adam and AdaBelief here. It seems AdaBelief slightly outperforms Adam for SAC model on both the half cheetah dataset and the Worker 2D dataset. We also provide the link to the code. So there are extra experiments for instability when training on. This is reported by user Alberto. So at the very first beginning, he reported that the result for AdaBelief in RN is quite terrible. This is because the gradient clipping is used in Adam, and gradient clipping just contradicts AdaBelief, because in AdaBelief we record the difference between GT and MT in the denominator. If we use gradient clip, this difference will be just very close to 0, and you will see a quite large explosion. And Breto just reported that disabling gradient descent AdaBelief converges faster than Ranger and SGD, but still AdaBelief gets some loss explosion randomly. This might be because that there are some extreme gradient in RNN trainings, such as vanishing or exploding gradient, which call this the denominator difference, GT minus MT, which cause this term to be really close to 0. So the division is dividing by a number really close to 0, and this might cause explosion. We don't have a good solution for this only in AdaBelief, but our Ranger version AdaBelief, which is basically combines look ahead with AdaBelief, it seems to be pretty robust to this kind of random explosion. And Brad reported that the modified Ranger, which is a Ranger AdaBelief optimizer, perhaps gets the best accuracy with half the epochs compared with to the regular Ranger, and also outperforms Adam. Yeah. This is an actual result by a blog where the author used this for transfer learning to perform text classification. The author implements his own AdaBelief in Keras. It's slightly different from the facial, but you can just refer to that as a reference. And the red curve is the accuracy for AdaBelief, blue curve is the accuracy for Adam. As you can see, in very early phases, AdaBelief does not outperform Adam very much, but as the training schedule goes on, when trained with much smaller linear rate, the red curve is almost always above the green curve. So which means AdaBelief outperforms the Adam. So again, please let me remind you of the general principle to use AdaBelief in experiments. So first is to check the code is from the official latest implementation. This is crucial because we might make some really important changes, and sometimes the non-official version perhaps could just set the default hyperparameters to a very different values. This would influence the result a lot. And the second point is to check all the hyperparameters. Do not simply use a default. The most important hyperparameter you need to check is epsilon. Remember that epsilon in AdaBelief is different from the epsilon in Adam. If SGD is better than Adam, use a large epsilon, 10 to the negative 8. If Adam is better than SGD, use a small epsilon, such as 10 to the negative 16. If you want to fine-tune it a bit, you can try 10 to the negative 12, which is in between. And also, if Adam W is better than Adam, which means the weight decouple is useful, then you should also turn it on in AdaBelief. This is turned on by default in AdaBelief implementations. And third point is, again, to check all the hyperparameters. And please refer to our GitHub page for a list of recommended hyperparameters for different experiments, as shown here. So thank you for listening, and also thanks to co-authors, contributors, and others for discussion. Please leave a message to me on GitHub if you encounter any issues or have any ideas on how to improvement. Thank you so much.